Thank you, Ajit, and thanks for inviting me here. And let me start with an apology. This is a CMB talk, and although I tried to make the title neutral, I thought of slipped in the CMB again. But the main idea is the approach that I'll be talking about may have implications for gravity wave backgrounds in the future, and I'll try to allude to that as I go along. So this work is, the graduate students involved in this work are Tuhin Ghosh, who's graduating this year, Rajiv Saha, who's been here in JPL for some time, and Pramod Samal, who's again just finishing up. Okay, so in cosmology, you know that we are in a pretty nice era where we have the good old cosmology, the Friedmann-Robertson-Walker universe, but we know the parameters of the universe quite well. And what's emerging is a standard cosmological model, which is a flat universe dominated by a cosmological constant with a nearly power law primordial spectrum. And we also, this part that we know about the cosmological parameters comes from trying to understand the mildly perturbed universe that we see in the microwave background and isotropies, evolving to what we see now as the large-scale structure in the distribution of matter, and this is via gravitational instability. So all the parameter estimates come from here, but there's this other leg, is where did the perturbations that perturb the microwave background come from in the first place, and our best bet is something like inflation. And in this context, and this thing is holding up quite well against observations. So inflation, for example, predicts homogeneous isotropic space. We see that. It predicted a flat geometry. We see that. And in terms of perturbations of the scalar kind, density perturbations, we see that the power spectrum is nearly scale invariant. And of course, the density perturbations, which are adiabatic and Gaussian. But one of the main things missing is something of interest to most of you, is the cosmic gravity wave background. And that's sort of the next goal in CMB, and that would come from polarization measurements. So this screen that I showed you, the cosmic microwave background, is a sky map like this one shown here. It has information in color about the temperature differences, the intensity variations on the sky, and on top of it you would have polarization information. Every direction that you look, the cosmic microwave background has a linear polarization, so you can put a pattern of sticks on it. And so you basically have a 3 Kelvin bath on which you have temperature fluctuations with an RMS of about 70 microkelvins, and the strength of this polarization signal is, there are two types. One is the gradient part of the distribution of sticks, which is called the E polarization, which is roughly about 5 microkelvins, and the B part, which is again the part which would be of interest to gravity people, is most likely to be sourced by the cosmic gravity background at intermediate multiples, and that has a range of predictions starting from 10 to 100 nanokelvins. And this means, since we have a temperature field and 2 polarization field, there are actually 4 angular power spectra that one measures. If we don't believe in any parity violating physics, if we have parity violation, you have 2 more spectra that are interesting. And this is just to set the background. When you measure the measurements we have till date about the temperature, E polarization power spectra, and the BB polarization power spectra, they sort of put together strong argument for inflation up to this point. So in this TE power spectrum, for example, you have this little dip, which is quite well mapped out now, which is on scales larger than what could have been causally connected at the last scattering surface from where the CMB is coming. And this is a proof of inflation. And if you look at the peaks of the EE power spectrum, they're exactly out of phase with the peaks in the temperature power spectrum, and this is expected if the perturbations are adiabatic. So what I'm trying to emphasize here is the basic predictions for inflationary models are sort of borne out by observations. The last thing that would really be very convincing is to see BB polarization, and the arrow should be somewhere here, where you should basically you would see a direct signature of cosmic gravity wave background. So the cosmic gravity wave background that you expect for inflation actually stretches on a huge range of scales. So this is cosmic scales here, and going down to terrestrial scales here, and this cyan band is the expected spectral energy density of gravity waves from inflation for reasonably generic models of inflation. Okay, I won't get into arguments on that, but this is kind of what is expected. What I wanted to point out is these are terrestrial detectors, LIGO, LISA, which would come up, and then this is pulsar timing. The closest in this game is probably the CMB polarization. I mean, if this is the level at which inflation has produced gravity waves, then we are a factor of maybe 5 or so away from detecting it. And what I should also emphasize, the importance of this measuring the gravity wave background is that it sort of, the amplitude of the gravity wave background sets the energy scale of inflation. So it would say a lot about what kind of model would work for inflation. Okay, and this is just to show you that the B polarization from Planck has some chance of seeing, Planck has some chance of seeing the B polarization from inflation, and may work out. So the main thing we are after is this clean probe of the CMB fluctuations in the sky. This is the CMB anisotropy map on the full sky, and this is what was obtained by the WMAP satellite. What you should realize is when you really map out the sky, you don't really see the whole signal. What you see is something like this at different frequencies, and this red band here is the galactic emission. And when you want to get this final map from which you derive all the cosmological information, you need to find a way of removing this foreground emission from your data set, right? And that is the problem at hand. I wanted to point out that there would be, I mean, so what is happening here is you have the cosmic background, fluctuations in the cosmic macro background, which are cosmic, which are coming from the last scattering surface, and here's the galaxy, which has got diffuse emission due to synchrotron and free, and also dust, which is kind of spoiling the show. A similar situation, okay, this is just to remind you what the foreground contaminants are: the synchrotron radiation at low frequencies, synchrotron free, and dust emission at high frequencies, spinning dust at low frequencies. So the game is to look at the CMB sky at different frequencies and try to remove this red band out of it. And you can see that the red band actually goes down with frequency in these WMAP channels, but it doesn't go down further when you increase in frequency. If you look at what you would see in Planck, you see that moment you go beyond 100 gigahertz, you start seeing more and more of dust emission. Something similar is expected for the gravity wave background, and that's what I wanted to point out in terms of the similarity between the two problems at hand. You would have a cosmic gravity wave background, but you would also have astrophysical gravity wave background, and you would need to find some way of removing one from the other. And so the astrophysical background are basically, you know, these pointed out here. So you have basically white dwarf binaries and neutron star binaries, which basically give you a stochastic background, which is first of all different, spectrally different from what cosmic background from, say, cosmic strings, string theory, or the typical slow roll inflation would be. Okay, so the main point is to try to remove this background from this. So this is basically the similarity between the two problems, and I won't really say much more than that about this problem. And this is just to point out that there could be interesting models where you actually have gravity wave background which is pretty large at high wave numbers, and in that case you would have a strong case for really finding methods to remove the astrophysical background to get at this signal. And this particular model is from particular kind of inflation model in a brain world scenario. Okay, so now I'm completely into the CMB part. So what do you usually do? Typically what is done is you have the CMB frequencies at which you are measuring the CMB sky. What you do is take maps of the sky at much lower frequencies where synchrotron dominates, or at much higher frequencies where dust dominates. You take the synchrotron map and the dust map, extrapolate it to the CMB frequencies that you're interested in, and cross correlate and remove the foreground emission. The problem, or the potential problem here, is that you need to extrapolate what you see at much lower frequencies. This is actually a 400 megahertz map, sorry, there's a typo there. So when you're going from say 400 megahertz to 70 gigahertz, we are sort of putting a lot of faith in astrophysical modeling of how synchrotron radiation intensity varies, and it is known that the slope with which the power varies is varies at different galactic latitude, for example. So it's always there's some level of uncertainty in an approach which uses templates to sort of remove the foreground emission, and this is particularly true for temperature fluctuations, and particularly true for polarization things, where actually we don't have very good models for what the astrophysical what the galactic emission is like. So this talk is basically about trying to use an approach which does not really depend on any astrophysical modeling. So what you really want to use is the fact that foreground emission is frequency dependent, whereas the CMB signal is not. So you just use the fact that the spectral variation in the foreground emission, whereas CMB is not, and you just use that known fact to try and clean up the CMB maps. And the idea again here is that if you look at the CMB emission at different frequencies, the CMB anisotropy fluctuations are completely achromatic, whereas the synchrotron or the dust have steep dependencies on the frequency. So how do we harness this method? So the idea is, when you look at the CMB sky map delta t, you can equally well represent it in terms of its spherical harmonic coefficients, ALM, and this ALM that you measure is the cosmic signal multiplied by the beam, the foregrounds multiplied by the beam, and the noise in your detector. And what you want to really use is the fact that while all these three A's depend on frequency, the CMB anisotropy is completely achromatic. Okay, the CMB true signal is actually completely independent of frequency. So the basic idea is to create linear combinations of map. So you create a combination of your multi-frequency maps, linear combination weighted by some W, to get this ALM, and you make sure that the weights add up to 1 over the frequency channels, so that your CMB signal is untouched. And then you basically look at the power spectrum of this combination. You would notice that the CMB signal drops out of the weight multiplication, whereas the stuff that depends on frequency does get weighed by the weights. And then this is a quadratic minimization problem. So you look for weights that minimize the total power. This is the approach we take. And the solutions for such a quadratic thing is well known. It's given here. Quadratic minimization problem. So you determine weights that minimize the total power, which means it minimizes the foregrounds, as well as noise to some extent, but that's not important. I'll get to how you remove the noise contribution a bit later. So this approach was first put forward by Tegmark and Iftekhar, and also done for WMAP first year data, but to only create a foreground clean map. But if you take the power spectrum of that map, the noise autocorrelation actually peaks and picks up at large L's, and you really can't get the CMB anisotropy power spectrum from that approach. So what did we do different? What we did different is to notice that the two K and Ka bands, the low frequency bands of the CMB, are essentially, you can look at them as low frequency measurements of the CMB sky. Then there are two difference assemblies at 41 gigahertz, 2 at 61, and 4 of them at W band, which is 94 gigahertz. So these 4 you can combine pairwise to make 6 maps at 94. So you have 6 maps at 94, 2 at 61, 2 at 41, and 2 at 23 and 33. And the idea is to create linear combinations of these difference assemblies and not really combine all the information that you have in the frequency into one single map. The advantage there is, if you look at this simple thing, so you have these many possibilities. So you can create 48 linear combinations, picking up one from each of this 6 to possibilities. And so you create 48 foreground clean maps. And the main advantage here is you can now identify in the 48 maps pairs of maps which don't have a common difference assembly. So they don't have a common noise channel. So if you cross correlate the power in the 2 maps which don't have a common noise assembly, then the noise drops out, because cross correlation noise drops out, so you don't have noise. So you have removed foregrounds by linearly combining, and you remove the noise contribution by cross correlating maps with no detector assembly in common. And this gives you, these are the 24 crossbar spectra from those 48 maps, and if you just put them on top of each other, you can see that you get a roughly good CMB, recover the CMB angular power spectrum quite well. And this is what we did for the first year and third year data, and we could show that you get angular power spectrum which is a good match to what WMAP team got by template based foreground removal. So this completely model independent way of removing the foreground emission works definitely as well as the template based method. Okay, this is for first and third, and this is for the 5th and 7th year data. So you can see that the error bars become smaller at larger L with number of years.
I'm missing the basic idea. Can we take a simple example? Just imagine there are 2 points on the sky and 2 frequencies at each point.
Mm-hmm.
There's 4 data points. So how would we do this procedure?
No, so basically what you're doing is you have, depends on how many components you want to remove, but so this is, you can do it in the real space. So you have you have measured the temperature at one point in the sky at different frequencies. Okay, so it has a constant contribution from the CMB signal and a varying component from different from the foregrounds. So it is like fitting a varying component and a constant. But what we did is in the harmonic space.
I want to do this. I'm missing one point. So any function you can write as a constant or some varying thing. So there must be a little bit of that information on it. You find that constant.
No, so okay. So let me go back. So see, we make this linear combination in ALM space. When you take the product of ALM star, you basically have a constant piece which is factoring out because this thing does not depend on frequencies at all, and you have set the weights to add up to 1, right? So the weight into something which does not depend on the frequency channels. Okay, so there's a WI sum which adds up to 1. So this is the constant piece plus a piece which is quadratically varying on the weights, and you now solve for weights which minimize this combination. So you've really got a constant thing with a quadratic thing that depends on the weights, and you find weights that minimize this combination. Sorry, maybe, okay, so this is with the 5th and 7th year data, and just to point out the third peak shows up. And then after this, the main problem was, challenge was to go and try to get the polarization power spectrum out in the same way. The real challenge with the polarization power spectrum is, if you look at the power spectrum, this is the signal that you're after, and this is the noise floor for WMAP, these lines here for different frequencies, these flat lines, and this was believed to be the foreground contamination at different frequencies. You can see that it's over most of the range of the angular scales, you have basically strong noise and foregrounds both dominating at the same point. And here the method would have problems because earlier you're depending on the different dependence, the dependence of on frequency of the foregrounds to remove the foreground emission. Here you have noise which is equally important, and that spoils the determination of weights. Okay, so this was a showstopper for some time till we all realized that the foreground actually was overestimated, and the foreground was not really as bad as this, but this is the Planck sky model foreground earlier version. Later version it's significantly lower, and the problem could be tackled to some extent. So we went ahead and used our method, and this is the angular power spectra for the CMB temperature, E-polarization and E-polarization power spectra measured by removing the foregrounds just by making linear combinations in the same way that I discussed for the temperature earlier. And here I should point out what we really had to do is, because noise dominates on the same scales as the foregrounds, the foreground cleaning is not as good and there's a bias. So this is these power spectra that we obtained recently actually have the problem that there is a bias correction that you have to make based on simulated foreground maps. So you simulate a lot of CMB sky with foregrounds and you ask how well does this method works, and what is the bias, and you estimate the bias and take it out and then measure this. So this is a little unsatisfactory in that respect. Pardon?
So we are saying that in this particular case,
not overall. There's a L-dependent bias that you take out. So what we did was made many Monte Carlo simulations, cleaned all of them in the same way, and we found that there's offset from the signal because of the given foreground level, right? So the bias correction depends on your Planck sky model that you use, and of course on the theoretical model of CMB. So it has some dependencies of that kind, the bias.
you are not modeling the spatial variation. That doesn't affect you.
No, here we don't model that at all.
And it does.
No, it doesn't matter. In fact, I don't have slides to show that. I should have probably. We can actually also take out the foreground. You can, just like you estimate the CMB power spectrum, you can also estimate the foreground power spectrum, again by cleaning the, removing the CMB part and estimating the power in the foregrounds, and you can make foreground maps, and we do recover the same kind of spectral variation in the stuff that we have thrown out. So you can ask what have we thrown out, and it happens to be a thing that has synchrotron with the given power spectrum. So that's a paper we have published. Okay, so this method, as I said, has a bias. So this is the level of the bias. So you see, you make a reasonably large correction, bias correction at these multiples, and that's kind of always iffy. And in particular, if you look at the CMB E power spectrum at low multiples, you see that there are points where we differ from what the WMAP team estimates by significant amounts, the three pointed out here. So the question to ask was, are these differences here, or this level of bias correction, how reliable is that? Is there a way to find a method where we don't have to make this bias correction? So that we find is pretty easy to do. So remember, we had these 24 pairs of linear combinations of maps that have no common detector assembly. But what we were doing is we are taking the clean maps and finding minimizing the autocorrelation power spectrum of these clean maps, right? But instead, what we could do is directly look at the cross power spectra of a combination C and C bar, which do not have a common detect assembly. So you look at, instead of minimizing CLCC, you minimize CLCC bar. So always minimize the power in the cross correlation. The advantage here is, if you remember, this quantity that I showed you earlier in the ensemble had a CL from foreground plus noise, but here it has the CL only of the noise. So if I minimize the weights, I am now guaranteed to get weights which only respond to the frequency variation of the foregrounds and not the noise, because the noise has been killed off in the cross correlation of C and C bar. So this is a method which we call DAPC. The earlier one we used to call IPSC. And so this method, the test for that was to check whether how sensitive is this method to different levels of foreground. So we already had two predicted levels of foregrounds, which was the Planck sky model version 1.1 and 1.6. They're quite different. 1.1 predicts much higher level of foregrounds, and you could ask, when I use this method, how sensitive is my bias to the two different foreground levels? And what is interesting is you find that the estimates are not really that sensitive to the amount of foregrounds that you put into your simulations. And I mean, again, I don't have a comparison, but for the previous method there will be a huge difference in the amount of bias that you have to correct for the two foreground levels. And this is the EE power spectrum that you get from this method for the WMF 5-year data. So this is comparing WMF 5-year using the previous method, using our new method, and we find that this is much more consistent with the signal that is expected, LCDM signal, than what we get. So we overcorrected in the bias subtraction here. And also these discrepant points are much closer to what you expect from theory in this DAPC method, because now we don't have noise playing a role in determining the weights. And these are sort of preliminary results we have now for the 7-year data. This is the CMB-TT power spectrum from the DAPC compared to the WMAP. You should ignore these points here, because at low L's the WMAP estimate is a maximum likelihood estimate, whereas our estimate is still a master kind of quadratic estimator. And so this is for the TT, this is for the EE at low L's, and this is how well we sort of agree with the WMAP guys. And this is again for the EE power spectrum in large bins, and this is the TE power spectrum. Again, there are certain issues with low L's, and that's why this label of preliminary. Okay, so then of course the next thing to think about is how well can this method be used for Planck. So Planck has the advantage that in WMAP you had only frequencies running from 30 to 100 gigahertz, but Planck has a much broader frequency coverage, and that would allow you to sort of take out foregrounds much more reliably in this case. And besides, this is just, maybe most of you know about it being here, the Planck has about 3 times the angular resolution of WMAP and 5 to 20 times the sensitivity of WMAP, and so it's would get you the primary CMB anisotropy up to cosmic variance limit, and polarization that you measure would be as good as the CMB, as the temperature polarization that WMAP has got. And as I said, it might be lucky to see some BB signal at low L's, which would be a gravity wave thing. So Planck, roughly this is the current state of CMB angular power spectrum, where you can see that you have mapped out the angular power spectrum up to 2000, or even actually further to 3000, and you're seeing different peaks in the CMB power spectrum. This is what Planck alone would get. This is WMAP plus few other experiments together, which gives you this angular resolution, but Planck alone would get you something like this, or better. And this method can be used again by either using all the channels together, or you can break it up into 2 sets of channels and use that use this cleaning at 2 different, a high frequency cleaning and a high frequency cleaning and a low frequency cleaning to get 2 sets of maps. It's sort of gloss over this, but there are issues about how to exactly to how many channels to merge at every frequency, and there's a optimization that is required, and there are various considerations of as you merge channels within a frequency, you of course decrease noise, but you lose out on the number of cross correlations that you can make. So there's a trade-off that you need to worry about. But in general, if you just take these multi-frequency maps from Planck at Planck resolution, the foreground clean maps are extremely good to the eye, and this is something which is quite promising. And this is, for example, an input sky map that you put in, then add foregrounds to it, and then make the measurements at different frequencies of Planck, recover it, and you can see that visually it looks very good. But there are always some residuals from the foreground of galactic foreground along the galactic plane. Here I am showing you a map which is particularly bad. But the question is, can we identify these things and use some other way of removing more power from the foregrounds? So we have been using till now the spectral difference between foregrounds and the CMB signal. That CMB was achromatic in against frequency, whereas achromatic and foregrounds are not. So is there anything else we can use? So there's an obvious thing, that is that if you look at this basically the galactic signal has a particular spatial structure on the sky. It actually is along the galactic plane, whereas the CMB is actually completely isotropic, statistically isotropic. And that is the kind of thing you want to measure and try to remove foregrounds using that aspect, the aspect that the foreground is not isotropically distributed, whereas CMB signal is. So that's another general consideration by which you can remove the two from each other. So if you have a galactic signal versus a cosmic signal, you could use this fact that the cosmic signal is rotationally invariant, whereas the galactic signal is not. And one measure of that is something called the bipolar power spectrum, which I'll talk about soon. But here, this is a bipolar power spectrum, and tell you what it is. But here is the bipolar power spectrum with error bars for a statistically isotropic sky, rotation invariant sky. And here you can see that this map can clearly tell you that this has got this residuals contaminating it. Okay. So how do we use the spatial structure of the galaxy? And the main point, again, as I repeat, the foreground violates statistical isotropy, whereas CMB signal does not. So you have to look for a measure for statistical isotropy. And one way to do that is to go into something called the bipolar representation. So what you do is you look at the fact that the correlation function is a two-point function on a sphere. So the correlation between temperature in two directions of the sky. And if it's isotropic signal, then this is just a function of the separation angle between the two directions. And that's why you can expand it in just the angular power spectrum and measure the angular power spectrum. If this symmetry does not exist, then this general two-point function on the sphere can be always broken up into bipolar spherical harmonics with a coefficient of this kind. And the main idea is to take a CMB map and measure these bipolar coefficients. The interesting thing about these bipolar coefficients is they are just generalizations of the angular power spectrum. Remember that the angular power spectrum is AL1 M1 mod square summed over M, whereas these are also measuring off diagonal correlations between different ALMs and weighted by a Klebsch. So these are these general bipolar coefficients that you would like to evaluate for your maps. And the main point is, if the map is rotationally invariant, then these bipolar coefficients are supposed to go to 0. So you don't have any power in the bipolar coefficients if the map is rotationally invariant. And this is just to show you that the bipolar power spectrum actually measures off diagonal information in the off-diagonal correlations between ALM and AL prime M prime. So if you're looking at the different multipoles, it's telling you that if your sky is completely statistically isotropic, you should not have any information here, and if it is, so all the information should be along this. So another way to put it is, when we are trying to clean the sky and it has foreground residuals, it would have power in these regions, and you would like to minimize these bipolar coefficients too, not just the angular power and not just the angular power spectrum, but also these bipolar coefficients together, and in determining those weights. So this is just to tell you that just like you have spherical harmonic decomposition of the CMB sky, you also have bipolar spherical harmonic decomposition. This can be done, measured, and just like you have angular power spectrum, you have a kappa L that measures deviations from statistical isotropy, and this is quite a sensitive measurement that you can make. And if you don't have any residual foregrounds, your kappa L should be consistent with 0. Or in other words, if you want to remove as much foreground emission as you like, you would also want to make kappa L's, you want to minimize the ALMs or the kappa L in your map. So this is an example of different levels of foreground residuals left in your clean map. So you have cleaned the map, but there's residual at different levels in this. This is a clean map, but this is a cleaner map. And what is shown here is this bipolar power spectrum that you can measure here actually can distinguish between the two maps, tell you that this is cleaner than the other. So you can turn this around and ask whether can I use this probe of residual foregrounds as a way to improve my foreground cleaning in my estimation of power spectrum. And you can, the way to do that is, okay, this is just to show you that these two have a very subtle difference. If I difference the map, these are the residuals. If I sort of zoom in the scale, then you can see that there is a strong pattern of residuals in the dirtier map than the clean map. So this is what we are trying to do now, is to extend the DAPC method by incorporating this extra information, that you want to also make your map not only free of not only remove the frequency dependent part, but also the part that is not rotationally invariant, the part that is most likely coming from foregrounds. So again, you have these two ALMs from different linear combinations C and C bar, and C and C bar are sort of have no common detector assembly. You can create bipolar coefficients. You can create these bipolar coefficients of these maps, and now you have again a similar minimization problems. So you have the C with these weights, but what is interesting is, earlier the weights on the two sides of this matrix had the same angular momentum L, right? So weights at a particular multipole L did not really care about the weight at the other multiple, so you can clean them L wise completely independent of each other. But when you're trying to minimize the cross correlation, actually WL and WL prime do talk to each other through the fact that there would be statistically anisotropic terms. So this is some work in progress. We don't have clear results at this point. So let me sort of summarize. So I talked to you about two different methods, for two related methods, which are internal estimation of the CMB angular power spectrum. The main thing is, this is done without recourse to foreground modeling. So you don't use any information about how the foregrounds vary with frequency. We just want them to vary as compared to the CMB signal. This evades the systematic problems due to modeling uncertainties or inadequacies, and this is potentially useful for CMB polarization, where the foreground uncertainties are larger. Our knowledge about the foregrounds, how they behave in frequency at different directions, is sort of less well known. So this method has been implemented successfully on WMAP 1 and 3 for the temperature, and for the polarization power spectrum for WMAP 5. For IPSC method, the previous method, we had to make a bias correction Okay, this is the part I didn't talk about, but the residuals are consistent with known foregrounds, and this is something that is reassuring, that whatever we are throwing out is actually consistent with what we believe is the foreground emission. We have analytic understanding of biases, and the main problem with the previous method compared to the later one was that for the polarization power spectrum, if noise also is important in the same at the same angular scales where the foregrounds are important, then noise actually spoils the weight determinations, and sort of it affects the weight determinations, and that's why you get a bias. We get around that problem by sort of minimizing the power in cross correlation power spectra. This is something in progress, but we have results for WM7, preliminary results. So now the next step is to exploit, so this method exploits the spectral dependence of foreground emission versus the cosmic background, cosmic signal, whereas now we can go further and try to use the spatial structure of the galactic emission versus the cosmic isotropic signal, and try to minimize that power and get possibly a better estimate of the better model independent estimate of the CMB power spectrums. So for all of these, of course, what's interesting is to try and look for appropriate schemes for Planck. Okay, I'll stop here. Thank you.
Yeah. We can have some questions before we have ice cream. I would like to ask you something. One of your first slides showed this idea that the sea is very balanced with the experiment, how the programs behave in different ways.
Mm-hmm.
But of course, this is after having calibrated with it. So my question is, how much does it affect, or how much do you control mismatch in the calibration? Because this very tight assumption of constancy.
Right.
You may have programs coming to this constancy. And I know that at the end of your talk you are showing that there are some residuals for programs. So this may be a perfect. But if you assume some symmetry isotropic, how much is that affect, for instance, for other signatures like, I don't know, the cold spot, the cold spot that you have in the sea? So are you not sweeping away some features of the sea that, because after all, there's some pricing to be big?
Right. Okay, so the two parts to your question, right? So calibration is an issue. Yeah, I mean you have to. We haven't done it, but you have to worry about the fact that the calibration at different frequencies is different, and people have looked at it. So I know that there's work.
If you confirm that on the map, you will see an agreement because we're using the same calibration. Is that something that's
Right, and you're asking whether when we take out the spatial, when we are trying to minimize the spatial dependence. Rotation, there would be some CMB thrown out. It's the same way that some CMB is also thrown out with the foregrounds, because they have some map to map variations with so there are chance correlations with foregrounds that would make some amount of CMB signal, and that is what leads to these biases. So you can actually estimate what the level of bias that you'd get from chance correlations with CMB with noise, or CM foreground and noise, for example.
That sounds like that may be complicated further by scaling as well.
Pardon?
Scaling of the central structures that you're erasing.
Scaling of the protein?
If you have a smaller object versus a larger object, if you're not looking at the differences between those, looking at them kind of monographic.
Right. So yeah, I see your point. So what you're saying is when I do it in harmonic space, I miss out the fact that I'm using the same weights at different regions of the sky, right? I mean, so what is actually done, which I again didn't get into, is the sky in this method is actually partitioned into different galactic regions, and the galactic regions are, the ALMs are separately done. The ideal in this way would be to use something like a wavelet basis, and there is something this is possible to do in something called the needlet basis. So you can actually have sort of a compact support in space as well as in multiple space. So you can do the cleaning in wavelet basis. You can do this cleaning in any basis, and wavelet basis would be interesting because you sort of have weights that depend on regions of the sky and also multiples of the sky differently. But you're right, I mean in this particular way but it's surprising that it works, at least for the WMAP thing, it works to the extent that it does.
Looking around and use this method to sort of get a better understanding of the modeling uncertainties and the mechanisms. Regions can use this method.
Yeah, I didn't have these slides here, but should have put them in. So what you can do is actually ask what is it that you've thrown out at different frequencies, and then you take those estimates and again cross correlate and find out the power, for example, of the foreground that you have thrown out, the residuals that you've thrown out, or you can even make residual maps at different. So both of these have been done. So particularly we have foreground maps with cleaning done not in this basis but in needlet basis. So you can make a estimate of the foregrounds and then ask whether the foreground that we have now, does it have the same behavior that you expect from theory. And it turns out to be the case. I mean, for example, you can take those maps and fit a synchrotron power spectrum and you'd see that the index does vary on the sky roughly as the way that you see it or it's been seen in the WMAP data.